Section 3 is position and time. So we're finally going to get starting talking about a little bit of math here. So putting numbers in nature. We're going to make quantitative measurements, not necessarily qualitative. So quantitative and qualitative, something that we're going to be talking about a little bit in this class. So we need to use numbers a little bit. As we analyze a motion diagram, it's useful to know where an object is. So what is its position? And when the object was at that position, so the time. So we're going to be talking about position and time in this section. We begin by considering motion only along a straight line. So right now, we're just doing like one-dimensional straight line motion, okay? That's called one-dimensional. I will abbreviate it sometimes to 1D motion. A car on a road, traveling straight down the road. Airplane taxiing on a runway, okay? Elevators moving up and down. So it doesn't have to be just horizontal motion. It can be like vertical motion. We can be going down a ramp. That's also straight line motion, even though it seems like it's in two directions. It's actually still just one direction. We just look at it down the ramp, okay? Position is always relative. Now this is something that's a little bit tricky sometimes for people to wrap their head around. Position is always relative. Like right now, where are you? Well, you're here in this classroom, but you're also here in this town, in this county, in this state, in this country, on planet Earth, in our solar system, in the universe, right? So there's a lot of different ways you can answer that question, okay? The same thing is true for us in these problems. Position is always relative. So where you define your starting point is going to be really kind of crucial always on all these problems, okay? Where is the origin? Where is zero? Is it where I'm standing right now, or is it where you're sitting right now? That's a big difference sometimes for us in our problems, okay? Which way is up? Is it positive or is it negative? Is up negative ever? Well, maybe it would be convenient if up was negative, just because of the way that the problem is designed, okay? Maybe the axis doesn't need to be stationary. Maybe the axis needs to rotate with the object as it turns. So always position is relative, okay? And that is something that's going to be kind of mind-blowing as we go, all right? So we need to sometimes get away from what we've been learning from like the 8th grade, where you started to learn about the coordinate system and beyond, because it doesn't always apply to physics. All right, when we work with motion, we're generally going to have an origin, a fixed location where the position and or time is defined as 0. So we want to define the position as 0. We want to define the time as 0 also, okay? So we're working with more than just position in this class. When was time 0? Where was the position 0, okay? All right, so let's see what we can do with these. Take a look at the picture. Notice the direction. We have west to the left, east to the right. That's pretty standard. The origin is defined as the post office. Our position here is in this vehicle. Notice the scale, 4 miles from the post office to our position. It says your friend asks where you are, and you reply that you're 4 miles east of the post office, okay? Because of our reply, you reply that you're 4 miles east of the post office. That reply set the origin at the post office, and then our position, because of the direction west to east, our position was given as 4 miles east of the post office, okay? What did we have to do to give our friend our position? We had to give an origin, the post office, a direction, and a position, 4 miles east. Okay? If we didn't give those 3 things, our friend wouldn't know where we are. All right? We can also set up a coordinate system using a fixed point for the origin. As a math class, we can do this. Okay? So now the post office defines 0 as a number line. So now our car is at a positive position of plus 4 miles. And now we have this cow over here at a negative position now. That's negative 5 miles, okay? As we would do in a math class on a number line. You follow that?
Yeah.
Okay. The origin, though, is totally arbitrary. We can make it anything. We could have made the origin us right here and called this 0. But if we're driving, then the origin would be moving.
You want a fixed point.
You could like it to be a fixed point. It simplifies the math. Okay? The origin is arbitrary, so choose known natural locations. It's an obvious place at the post office. Okay? This is the symbol or coordinate used. So to represent positions along the axis, we would use X. The start of the race is a natural place for the origin. So if we started right here for our race, X beyond the starting point and 0 for the start of the race, perfectly reasonable in this case. Okay? All right. Like I said, the origin is totally arbitrary. You can make the origin anywhere you want it to be. Okay? And that is something that's a little different than math from previous classes. And that'll be something that takes a little bit of getting used to. All right. Motion along a straight line does not need to be horizontal, and I kind of hinted at that a minute ago. We can tip our axis to align and make it a one-dimensional motion problem. If we didn't do that in this picture, then we would have motion along the x-axis and y-axis at the same time, and that would complicate this problem. So what we do is we tip the axis, okay? Just think of putting the origin up here and dropping the x-axis to align with the motion of this person who's going down the ramp, okay? And now they're moving in a positive x direction, and it's solely one-dimensional motion, even though looking at it, it looks like two-dimensional motion, okay? It simplifies the math, makes it easier. Now, they are moving downward and to the right, but along this slope, they're only going 10 feet, 20 feet, 30 feet, 40 feet. If we wanted to calculate how far down they went in the vertical direction, we could set up a right triangle and do some Pythagorean theorem, okay? Yeah. But as far as the motion itself goes, they are simply moving in a one-dimensional way. You follow that?
Yeah.
Okay. Now, we also had this rock falling here. We don't need to be moving horizontally every single time. We can also drop something off a cliff or something like that, and that's going to fall straight down. And because it's going in just one direction down, that's also one-dimensional motion. So what we do here is we would define the origin as where the ground is, and then positive would be up. So we have positive up here. The rock would have started off maybe up here at positive 8 feet, and it's going to fall, and when it hits the ground down here, it will be at 0. So this is a little bit different than, like, we're going down the ramp here and going farther away from the origin. In this case with the rock, we're dropping down to the origin. Okay?
Yeah.
All right, so I kind of talked about this before. Is this a leisurely stop or a screeching halt?
We don't know.
We don't know. How come we don't know?
We don't know the
Right now, time measurement.
We have no idea what the time interval is. Without that, we cannot answer that question. All right? If the frames were taken 1 second apart, it's probably a leisurely stop. But at 1/10 of a second, 10 times faster, it's probably more like a screeching halt. So we just don't know, all right? So this sentence down here at the bottom is very important. To fully describe the motion, we have to indicate the time interval, okay? Without that, we are only really half doing the problem, okay? All right, so when do we start the time? So if we're interested in the entire motion of the car, we'd probably set time equal to 0 at the start of the motion diagram. That's a great place, okay? If we're only interested in how long did it take the car to come to a stop from the moment the braking started, we'd probably start time right there when the braking started. Okay? If we're interested in a problem where, oh, a deer ran out in front of the car, at this moment in time right here, from the moment that the deer ran out in front of the car to the time that the car came to a stop, for example, we would probably start time right here and then solve the problem to where the car came to a complete stop. Okay? Because then we care about a reaction time to here, and also how long did it take to come to a stop. All right? So now we have two problems. Reaction time, no braking is occurring, and stopping time, where braking is occurring. Okay? So in that case, you would solve the problem in two parts. Because no braking is occurring, that's a constant speed. Braking is occurring, not a constant speed. Make sense? Okay. All right. So what you need to do, and we'll talk about this more when we start solving problems, is ask yourself, what is it that I'm supposed to do here? What is going on? What is the problem at hand? If the problem at hand is just coasting time, great. If it's braking distance, great. If it's reaction time, okay, fine. If it's total stopping distance from the moment the deer ran out in front of me, I need that whole thing. How am I going to do it? Okay? So that's what you need to do. Stop and think before you do anything. What is it that it's asking you to solve? Then come up with a plan. Okay? And we'll get into that when we start solving problems. Okay, now change in position. The word for change in position is displacement. How far did I go? What was your displacement? We're going to be using that word a ton. So Sam is standing 50 feet from east of the corner of 12th Street and Vine. So 12th Street and Vine. Vine is here, 12th Street is here. The corner of 12th Street and Vine is our origin then. Okay? They said 50 feet east of that corner. So we go 50 feet. Here's Sam right there. Sam walks to a second point 150 feet east of Vine. What is Sam's change of position? Change of position. Yeah. So now Sam goes over here. He's 150 feet east of Vine. But what was his change of position? What was his displacement? How far did he move? He moved 100 feet. Okay? So mathematically, we would call this x sub I. X sub I is 50 feet. We would call his final position x sub f, and that is 150 feet.
And delta, delta.
Delta x is what we would say. That's change in x. Okay, delta represents change in. Delta x is going to be the final position minus the initial position. That's a formula that we will use a ton. And so you just do 150 feet minus 50 feet, and you get 100 feet. Now, we knew that. We did it in our heads. This is the first problem of the year. I'm showing you a couple of things. One, first thing is we're writing down what we know here. The second thing is we're writing down the formula that we're going to use here. The third thing is we're plugging in the numbers here, including the units. And the fourth thing is we're writing our answer. So now let's go back to what you wrote. Did you write down 50 feet and 100 feet? Did you write down the units? Here, did you write down the formula? And then here, when I wrote 150 feet minus 50 feet, did you write down the units? And then here, did you write down 100 feet? This is how we're going to operate in this class. This is not a math class. This is a science class, okay? We're going to write down what we know. We're going to write down formulas. We're going to manipulate formulas before we plug in numbers. We're going to write down the numbers, including the units, and then we're going to write down our answers. Okay?
Was it you or Cheatham who was like, you didn't put your unit and measure, you'd still mark it wrong?
Both.
For like half credit.
Both, but I wouldn't take credit away. Okay, what if Sam had walked back to the intersection instead? What would his displacement have been in that case?
Negative delta x equals 50.
No, it's.
Write down what we know.
So xi is 50 feet.
That's right.
So then xf is 0 feet.
That's right.
So then delta x equals 0 minus 50, which would be negative 50 feet.
I disagree.
But
Delta x equals x sub f minus x sub I equals 0 feet minus 50 feet
Equals 50.
equals negative 50 feet. Okay. In your explanation, what you missed was the formula.
Oh. Okay, so we need the.
We're gonna use the formula, okay? Gonna emphasize that over and over. Later on, when the problems get super complicated, using the formulas now is gonna help you later. It's gonna be very natural, and you're gonna see why. Okay, you'll understand. So in general, the change in any quantity is the final value minus the initial value. X sub f minus x sub I. T sub f minus t sub I for time. Okay? And if we're talking about y, because we're doing a vertical displacement, like we dropped a ball or something like that, y sub f minus y sub I. Okay? Just because we had x here doesn't mean that we can't translate that into something else. All right, so let's talk about change in time. So time intervals. Consider the motion diagram for a bicycle moving to the right at a constant speed. What is its displacement? And how long did it take to go that far? So the displacement first. We have the initial position, notice over here, final position over here. So we're going to say delta x equals
120 feet.
x sub f minus x sub I
Sorry.
equals
120.
Minus
120 feet minus 0 feet.
Yep.
Okay, so we have 120 feet. Good. Now, how long did it take to go that far? So we will say delta
X. Wait, no, delta T.
t equals
T sub
t sub f
minus
minus
F sub I.
t sub
T
I equals t sub f.
Is 6.
6
6 seconds.
seconds
Minus 0.
minus 0 seconds equals
6 seconds.
6 seconds. And you're sitting there going, oh my God, this is so painful. I already know the answer. Why do I have to do this, right? And I know, I understand. I want to do it the other way too. I just want to say the answer. But trust me, we're building a skill here so that later on, just even very soon, we're going to be doing problems where we're going to be using formulas and combining formulas, and I want you to start using this process now, okay? You got to trust me. All right, a time interval, delta t, measures this should say elapsed time. There's a D there. As an object moves from initial position x sub I at time t sub I to final position x sub f at time t sub f. And note that delta x can be negative. Delta t is always positive because as time goes on, t sub f is always going to be bigger than t sub I.
Because it's the only constant thing.
Time has to go on, right? Okay. Emily is enjoying a bicycle ride on a country road that runs east to west past a water tower. At noon, Emily is 3 miles, and notice the abbreviation, MI for miles, east of the water tower. A half hour later, she is 2 miles west of the water tower. What is her displacement during that half hour?
Negative 1 mile.
The first thing we're going to do is
Make our origin,
Delta.
which is the water tower.
draw a picture.
Oh, okay. So Emily, dot.
Nice level ground.
Do you want us to write a
Mine looks
get a
like
ruler
rollers.
and do it?
We have been given east-west.
We need a compass.
So we have probably west to the left, east to the right, right? West, east. Okay. And we got a water tower. Where do you want to put that water tower?
You can
The
put it in the
middle.
middle. because
Right in the
it's
middle
a
makes
river.
sense. So I don't know what kind of water tower is it. Is it old country water tower or is
I
it
was gonna do like
a
a newer,
modern?
I was gonna do like a
Yeah.
modern water tower.
A modern
ones where it's like
bulbous
bulbous
water
at the
tower?
top, It's like skinny legs.
Okay. Pretty good water tower right there.
That's pretty much what I did.
All right. So it says at noon. Why is at noon important?
Noon?
Yeah,
Because that's the starting point.
that's the starting time. She is 3 miles east of the water tower. So where is she?
3 miles.
3 miles
Right.
east
Oh,
of the water
right,
tower.
Right.
Over here. This is 3 miles. And what time is it?
12.
What time is it really though? For us.
Oh, this morning? Like right now?
This is x sub I.
Oh, there's the I starting point.
And so this will be t sub I equals what? Not noon,
At 12 o'clock.
not 12 o'clock,
Oh, what?
This is
Zero.
0.
Why?
Man.
Because that's the starting point.
That's our starting.
No, because it says when she's 3 miles away, it is noon.
Yeah.
So that's the information we're given. So why are we starting at 0 there?
Because then we
Because
can
that's
just go
what
half
time
an hour
our
later.
stopwatch is going to start.
Is at noon.
Uh-huh.
So we
Okay.
start.
Okay. A half hour later,
You get Katie.
she is 2 miles west of the water tower. So what do?
We drive a
0.5.
person.
At 2 miles.
2 miles over here, right? 2 miles west of the tower. So what is that?
Oh,
2 MIs.
XF.
X sub f equals
2 miles.
2 miles over here.
And then
Time.
T sub F
the
equals
time.
0.5.
T sub f
0.5.
equals, so you're saying a half an hour is 0.5?
Or are we doing minutes or are we doing hours?
Yeah, that's a good question.
Yeah.
So we need units on this time
If
then.
we're doing minutes, then we're doing this 30. If we're doing hours, then it'd be 0.5.
Yeah, I was thinking hours because it's.
They did say half hour.
Yeah.
Okay, so this is 0h and this is 0.5h.
And now we can do that.
Okay, now
formula.
the question I'm going to ask you guys is this 3 miles and 2 miles good? You like that?
No, we should put a negative
Negative
on the
2
2
miles.
You like a -2 on the miles. I like a -2 on the miles also.
Because if the
Now we're
water
calling
towers
the
are
water
origin at
tower
0.
0.
We should get a little person doing a bike.
No.
So then it would
All right.
be
What is her displacement?
delta T equals
We need displacement, so that's delta
X.
x equals
X sub F minus X sub I equals 3 miles minus.
x sub f
Oh, yeah.
-2, so it'd be 1
-2 miles
There we go.
minus
minus
Wait, is it,
Minus
no, it'd be
3
one.
miles.
3 miles
Oh, yeah. Which would be
Equals-
-5
-5
miles.
miles. Okay, now this problem did not ask us anything about time. It just asked us about displacement. So all of the time stuff didn't matter at all.
Oh, okay. So
Okay? But putting it in the picture didn't hurt us. Okay?
She's cooking.
Yeah.
Going 5 miles in 30 minutes?
All right.
That's 10 miles an hour.
La Sarah starts at a positive position along the x-axis. She then undergoes a negative displacement. Her final position is what?
She undergoes a negative displacement. Her final position is.
It could be, it's C.
It could be,
Because
it could be both, it could C, because we don't know how big of, because as long as it's a negative displacement, that means that she's moving back towards the origin, but we don't know how much.
We don't know how
If she's
long.
at, she could be
Yep.
at 10, she moves back 2, well, then she's still, in a positive
That's right.
displacement, but
So she's moving this way.
We just
Don't know how long she was moving that way for, how fast or whatever. So she could be here, she could be here, she could be here, we just don't know. So it could be either positive or negative. That's correct. Good job.
Yeah.
All right, and that is it for this section.